Hello, welcome to Econometrics Melody. In this video, we'll discuss about the moment generating function of random variables. And before that, let us see some of the useful formulae from derivatives. So derivative of x to the power n, this is equal to n x to the power n minus 1. A simple example, if we need to calculate the derivative of x to the power 7 with respect to x, that is equals to n 7, and then x to the power n minus 1, 7 minus 1 is 6, so we get it is 7x to the power 6. The derivative of e to the power x with respect to x is e to the power x itself. This is a very interesting property where e is our Euler number. Similarly, the derivative of the sum of the function of x with respect to x is equal to the sum of their derivatives. And let us see, this is our chain rule. The derivative of e to the power x square with respect to x. First of all, we create the same base derivative of e to the power x square, and we take the derivative with respect to the x square, and further we multiply it with by derivative of x square with respect to derivative of x, and this cancels out and we are left with derivative of e to the power x square divided by derivative of x. And let us see our product rule. The change in x into y, the product of x and y, this is equal to x into change in y plus y into change in x. And this is an interesting property between derivative and expectation. So derivative of expectation is equals to the expectation of derivative. Therefore, derivative of expected value of x square with respect to x, this is equal to the expectation of the derivative of x square with respect to x. So this is somewhat related with this property, that is the derivative of sum is equal to the sum of the derivatives, and our expected value or the average value is also related with summing the product of probability and the individual observations of a random variable. Now let us move into today's topic. It is moment generating function of the random variables, and we express it. So the function of t, we have a function of t that is equal to the expectation of e to the power tx, and where x is our random variable. So this is our moment generating function, and this is the function of t where we calculate the expectation of e to the power tx. So we know how to express the expectation when the variables are discrete random variable and continuous random variable. Expectation of, let us consider this entire term is x, the sum of all the x, and we take the probability of that x, so this into probability, and we can write it as xi, where I it is from 1 to n, and we sum it for all the x. Now let us see for the continuous random variable. So we integrate it from its lower bound to upper bound. Let us take it minus infinity to infinity, and let us take this entire term is our x, and we have the probability density function. It is fx, and with respect to x. Now we have seen that our moment generating function, and that is the function of t, and we take the expectation of e to the power tx. So this is our moment generating function. So now let us take the derivative with respect to t, derivative of this our moment generating function divided by dt, and we can express it as, so first of all, we know that derivative of expectation is equals to the expectation of derivative. So let us write expectation, and inside we take the derivative of. Now let us apply the chain rule. This is equal to this term and this term, it cancels out, so ultimately we are left with the same thing. The derivative of e to the power x, here it is e, so we have the same derivative, because derivative of e to the power y with respect to y, that is equal to ey into, now we have t over here, so we are left with x only. So this is our first order derivative. If we take the first order, evaluate the first order derivative when t is equals to 0, then we are going to get the first moment, x into 1. So this is equal to expectation of x. So when setting the first order derivative of our moment generating function and evaluating it 0, we get the first moment of the random variable. This is equal to mu. The expectation of x is equal to mu x. Now let us see what happens if we calculate the second order derivative of our moment generating function. This is our first order derivative, and we have seen that that is equal to, now let us take the derivative one more time. That is equivalent to the second order derivative. So this is equal to, let me do it a bit directly. We have expectation of x into e to the power tx, and we are taking derivative with respect to t. So this is equal to expectation of, and we are simply going to take the derivative with respect to t, x over here, x e to the power tx, because the derivative of e to the power tx with respect to derivative of t, this is going to give us a derivative of e tx. Let us make the base the same. So we have tx into derivative of tx and with respect to derivative of t. So this is e to the power x. So derivative of e to the power x is e to the power x itself. So we have t over here, the power is 1, and the formula for dx to the power n divided by dx, this is equals to n into x to the power n minus 1. So if we apply that formula, so we are left with n is 1 into t to the power 1 minus 1 is 0, that is again equal to 1, and we are left with x. So the second order derivative of our moment generating function, that is going to give us, similarly, if we evaluate it at 0, e to the power x square. So it gave us the second moment. From here we can calculate the variance, because we know that the variance of random variable x is equal to, so let me write it in terms of moment generating function. So this is the second order derivative of moment generating function evaluated at 0, minus this one is the first order derivative of moment generating function evaluated at 0, and we can calculate its square, therefore variance of x. And if we follow this process, then we see that the nth order derivative of a moment generating function, when it is evaluated at 0, then this is going to give us nth moment of that random variable. So we see that the moment generating function, this has some sort of one-to-one correspondence with the distribution of x. Let us say random variable x, this has certain distribution. Let us say it is a normal distribution for our simplicity, and this normal distribution we can define it in terms of its parameters. Let us say for the first moment mean or average, and its a second moment we can call it is the variance moment generating function, and we have a distribution of the random variable to this side, and it seems that the moment generating function has one-to-one correspondence with the distribution of random variables. So we can say that moment generating function, it actually uniquely defines or determines the distribution of the random variable, because we have seen that the first order derivative of this moment generating function, this is equal to mu, and the second order derivative when evaluated at 0, this is going to provide us information on the second moment, so that is going to help us calculate the variance. And also we have seen that the nth order derivative when evaluated at 0 of that moment generating function of the random variable, that this is going to give us the nth order moment. Now let us see another interesting property. So let us take two random variables x and y, and they are independent. So once they are independent, so let us see a review. In case of probability, when two events a and b, they are independent, then we can express the intersection of their probability is the product of their individual probability, and the expectation counterpart for this is equal to. Also, if we want to calculate the covariance of xy, due to this property we can further separate it. So we can say that the covariance of two independent random variables, that is always equal to 0. Now let us see what happens. So we are going to create a random variable x plus y. Let us say it is equal to z. So the moment generating function for the random variable x, and similarly the moment generating function for the random variable y. So what is the moment generating function of z by the same principle? This should be equal to, now let us expand this and see what happens. Z is equals to x plus y. Again, this is equal to expectation of e to the power tx, and if we apply the property of index, so this is equal to e to the power ty, because when the base are same, then in case of multiplication we add the index. And as both x and y are independent, then we can see this product within the expectation. So if they are independent, then the expectation of the product can be expressed as the product of their individual expectation. And let us apply that properties. And this is further equal to, this is our moment generating function of x, and this is our moment generating function of y. So we see that the moment generating function of the sum is equal to the moment generating function of the product. So we can conclude that the moment generating function of the sum of the random variables, so that is equal to the product of their individual moment generating function. And let us reiterate the property that we have mentioned already. If we have moment generating function over here and we have a distribution of the random variable, moment generating function has the one-to-one correspondence with the distribution of the random variable, and MGF or moment generating function, it uniquely determines the distribution of the random variable. Similarly, we have seen that the nth derivative of the moment generating function, and when we set it to 0, then we get the nth moment of the random variable. So this concept is going to be very useful in our generalized method of moment. In that case, we equate the moment of population with the moment of sample, and then we derive the value of the estimates, which we will explore in our coming videos. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.